This is a video for the review for the second test. Again, the review that I'm giving you for the second test is the vocab that was on this half sheet, and then you had a second sheet. Now this is all out of your book, so this is on page 64, I believe is where this starts. I think this is page 64, the vocabulary review, and then the second page starts on page 66 and 67 of your textbook. But again, I gave you these handouts so that if you want to just write on the handouts, that's fine. You didn't have to go into the actual textbook. Now, the problems that I'm having you do in this review are questions 2 through 8, and then the second part goes from question 27 all the way through 46. You are not to answer the last question, 47. That has an indirect proof. Again, this question right here, we did not cover indirect proofs. You will not see indirect proofs on the test. Now, some of the proofs that are on here are a little bit harder because they are proofs from scratch. Again, I will go through them, but you won't see a proof from complete scratch like you have on here. You will have fill in the blanks. So again, I gave you kind of an outline on EDSB. If you look at the outline that's posted on EDSB, that's the outline that I use to make the test. So it gives you a good idea of what types of questions you will see on the test. There is lots of vocab. In fact, I think almost every vocab word that's used in, not just here, but all the vocab words I gave you on the vocab list are used on the test. Now, not every single postulate and every single theorem gets used, but the actual vocab, the vocab words parts on there, I would say almost every single one of them gets used somewhere on the test. And it is very important that you know your vocab, especially when you get to your proofs. You have to know your vocab, you have to know your properties, your postulates, your theorems. Again, it's very important that you have a good understanding of those, not only for this test, but throughout the rest of the year. So make sure you study those. Okay. Going through the vocab part of this, starting with number 2, choose the correct term to complete each sentence. So the first one, a statement accepted without proof is a postulate. Again, postulates don't have to be proven, they're accepted as true. Arriving at a conclusion by observing patterns that would be inductive reasoning. Keyword there, observing, so that's inductive reasoning. The next one, a blank is a combination of a conditional and its converse. So when you write a biconditional, that is a combination in the format if and only if. So this would be a biconditional. Again, you can only write a biconditional if you have the same truth value for the original conditional and for the converse. So again, that's why you're able to write this combination of a conditional and its converse, because they share the same truth value when it's a biconditional statement. And you use the words if and only if in the middle of the two statements. Number 5, according to the blank, if a conditional statement and its hypothesis are true, then its conclusion is also true. So if you're given a conditional statement and a hypothesis that are true, then you come up with your conclusion based off of that. That is law of detachment. Again, so you're given one full conditional statement and you're given a hypothesis, and then you come up with the other part of the conclusion based on that. That is law of detachment. A conjecture that has been proven is now a theorem. So again, theorem is after you've proven a conjecture, it becomes a theorem. So you use a proof to come up with theorems. A statement of the form, if not Q, then not P, is a blank of the conditional, if P, then Q. So this is an inverse when you add in the word not. You're negating both statements. But then not only did we negate them, we also switched them. So this was Q and P, whereas originally it was P, then Q. So switching them makes it a contrapositive now. So again, converse is when you only switch. Inverse is when you only negate. Contrapositive is when you do both. So since we negated and we switched, it was a contrapositive. You use blank when you logically come to a valid conclusion based on statements. So, let's see, did that one. Deductive reasoning, again. So when you logically come to a valid conclusion based on given statements, that'd be like going through a proof. So again, this is our deductive reasoning. Again, you can also say it's reasoning based on facts. So based on statements, based on facts. Deductive reasoning. All right. Just to recap over here real fast, if you're given a conditional, so I'm going to add this on over here. If you have a conditional and you had if P, then Q, the converse switches, so if Q, then P, the inverse negates both statements, but in the original order, so not P, then not Q. And then finally, a contrapositive does both negating and switching. So if not Q, then not P. And finally, you could also write a statement as a biconditional if the conditional and converse have the same truth value. For a biconditional, you can write as P if and only if Q. So again, that's some shorthand notation that you should be familiar with. And if you're not, make sure that you are. Okay. Going through the next page, so this is now page 66 from the book. Again, you can just use this paper if you want to. But the first part of this, 1-4, was all about inductive reasoning. So again, there's some examples over here, just to refresh your memory about some things. We're going to go through the practice and problem solving part of this. So use inductive reasoning to find the next two terms in the sequence. Again, inductive reasoning is when you're making observations, you're identifying a pattern, and then you're applying that pattern. So you're coming up with a conjecture. That's, again, the inductive reasoning part of that. You come up with that conjecture, that prediction. So now apply it to this. We have 1, 2, 6, 24, and 120. Well, I can see that from 1 to 2, the difference there is 1. Then from here to here, the difference was 4. The difference then after that was a lot bigger. So I don't know if we're going to be adding something. Let's try multiplying. From here to here, we multiply by 2. Then we multiply by 3. Then we multiply by 4. So I see a common pattern. The number that we're multiplying by each time is going up by 1 every single time. So now if I find the next value, multiply this by 6, we would get, that's going to be a big number, 0, that's going to be 12, so 2 carry a 1, that's 720. And then the next term, we multiply by 7, and it's going to end in a 0, we have 4 carry a 1, times 7, that's 49, 49, add the 1 back, that's 50, so 5,040. So our two next numbers are 720 and 5,040. Again, multiplying by 1 more value each time. On the next one, let's see here, we go up by 2, then up by 3, then up by 2, then up by 3. Seems to follow the same pattern. It keeps going, plus 2, plus 3, plus 2, plus 3. So now if I go back to plus 2, the next number would be 15, plus 3, the next number would be 18. So those would be our next two numbers in that sequence. Let me zoom in on this a little bit. So on the next one, 2, 5, 9, 14, and 20. Well, I see a difference there of 3, then 4, then 5, then 6. So plus 3, plus 4, plus 5, plus 6. So now if I add 7, we're at 27. If I add 8, we're going to be at 35. So 27 and 35 would be the next two numbers in that sequence. On this one, we have 17, 21, 25, 29, and 33. The difference here is 4. The difference here is 4, 4, 4 every time we added 4. Now, I try to make this a little bit easier on the test. I'll tell you that here we're doing number patterns. I try to make it so that you're given shapes. Kind of more like the example that was over here. So just keep that in mind as you're studying. Instead of doing this type of pattern, I did end up doing shapes. Alright, on here, so keeping this same pattern going, this would be 37, add another 4, and we're at 41. So 37 and 41, next two numbers in the sequence. Find a counterexample to disprove each statement or support it with 4 examples. So again, if you can find one counterexample, then it has to be false. All triangles have 3 congruent angles. Well, the only type of triangle that's for is what's called an equal angular triangle, meaning all the angles are equal. So that would be false, because if I had any other type of triangle, let's do a right triangle, would be an easy one to show, because in a right triangle, you can only have one right angle, because all 3 angles have to add up to 180. And if this is 90, subtract that from 180, the other 2 have to add up to 90 still, and I can't have a 0 angle, so just between these two, they're not going to be the same as this one. Again, you can only have one 90-degree angle. Same thing would go for an obtuse triangle. If you showed an obtuse triangle, again, you can only have one obtuse angle in a triangle, so you couldn't have all of them the same. If you drew any type of scalene triangle, all the angles are going to be different as well. So my example, or my counterexample here, is of a right triangle. So again, that is false, and that would be my counterexample. If p is an even number, then p plus 12 is even. Right? Well, if p is an even number, so again, only talking about even numbers, and I add an even number to it, that should just give me another even number. So if I do this with a couple different numbers, let's say 2. 2 plus 12 is 14. Let's do a bigger number, 10. 10 plus 12 is 22. Go even a little bit bigger, 52 plus 12 equals 64. And I'm going to go even bigger, 1,120 plus 12 is 1,132. All even numbers, because again, if you have an even number to start with and you add another even number to it, you should get an even number. So this was true, and there's a couple examples to go with it. Number 33, construct arguments. Explain why only one counterexample is sufficient to prove a statement, to disprove a statement, but one example is not sufficient to prove a statement. Well, let's go back to the idea of all triangles have 3 congruent angles. I have a couple of examples that would work for this. I could say on 31 that a regular triangle would have congruent angles, an equal angular triangle would have congruent angles, and an equilateral triangle has congruent angles. Even though I came up with those 3 examples, there's plenty of false examples or counter examples that would disprove that statement. So again, if you can find one thing to disprove it, it is automatically false. So again, doesn't matter the number of examples. If there's one counterexample, it is false. All right. So now on the table shows how much Jack saves in his bank account each week. So let me scoot this up so you can see a little bit better. At this rate, how much will he save on week 10? So looking at the numbers here, this goes up by, it looks like 175, and then it goes up by another 175, and then up by another 175. So every time we're doing plus 175. So if we keep this pattern going out to week 10, so 5, 6, 7, 8, 9, 10. I'm not going to figure out every single number in between, but we would have from there to 5, from there to 6, from there to 7, from 4 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9, 9 to 10. Each one of these represents an increase of 1.75, and there's going to be 1, 2, 3, 4, 5, 6 more increases. So 6 times 1.75. And then we'll add that to the 7. So add that back to 7. And we should be able to find our answer without finding every single one of these. Now, if you want to plug it in and just add 1.75 every single time, that's fine. 6 times 1.75, let's see, 6 times 5 is 30, so carry the 3. 6 times 7 is 42. Again, we carry the 3, so that's 5, carry a 4. 6 times 1 is 6, and then again we had a 4, so we're going to have to add that back, so it's 10. So we have 10.50 that we're adding back on to the $7 that was on that last number. So that's going to be a total of $17.50 at week 10. All right. The next one is all about conditional statements. So again, conditional, knowing what parts the hypothesis, conclusion, how the converse, inverse, contrapositive, biconditional relate, what their truth value is. Again, these are all important concepts from 1-5, all on the test. For each statement, write a conditional and a converse, inverse, and contrapositive. A number that is a multiple of 4 is a multiple of 2. Well, again, they want for each statement, write a conditional, the converse, inverse, and contrapositive. I need a little more space than what I have on this paper for this one. So let me grab a scratch piece of paper. Number 35. The conditional, again, we're writing this in the if-then format. So the original statement was a number that is a multiple of 4 is a multiple of 2. So we want to make sure it has the same context. So if a number is a multiple of 4, then it is a multiple of 2. Does that have the same context? Well, a number that is a multiple of 4 is a multiple of 2. Really, the way this is phrased, the multiple of 2 should come first. So let's check our meanings. If a number is a multiple of 2, then it is a multiple of 4. That would be a correct way of rephrasing this. If a number is a multiple of 2, then it is a multiple of 4. Let's see. Let's double check it and make sure that the truth value is the same. So that's how you can really guarantee that you have the same thing. Because sometimes when it doesn't have an if or then in it originally, it makes it harder. So I just tried this as a conditional. I combined the two statements. Let's see if our truth value lines up. So a number that is a multiple of 4 is a multiple of 2. I would say that that is a true statement. Let's see if this is also true. If a number is a multiple of 2, then it is a multiple of 4. Well, could we have other numbers that are multiples of 2 that aren't multiples of 4? Yes. So I actually ended up writing this backwards. The first way I said it initially would have been the correct way. So if I would have left it in the same order that was there, then the statement would have had the same meaning and it would have been true. So let's rewrite the conditional. So really the conditional should be if a number, now there's a reason why I'm not erasing this yet. If a number is a multiple of 4, then it is a multiple of 2. So this actually has the same truth value as this. These are both true statements now. And I didn't erase this because, yes, it's not the conditional, but I switched the if and then, so I could now just call that one I wrote first the converse of that original conditional statement. Now, conditional and converse don't necessarily have to have the same truth value because they are not always going to be logically equivalent. If they were logically equivalent, then we could write it as a biconditional. In this one, this statement ends up being true, the converse ends up being false. They are not logically equivalent. So this could not be written as a biconditional. Now if we want to do this as an inverse, we have to negate both statements. So negating the original statement, if a number is not a multiple of 4, then it is not a multiple of 2. And the contrapositive would switch and negate. So, got to switch them around. So in the same order that we had the converse up there, but then add in the word not to negate both statements. So if a number is not a multiple of 2, then it is not a multiple of 4. So those would be our 4 statements. All right, for the next one, instead of writing it all out to save a little time, I'm just going to say these out loud. So, Kiona jogs 5 miles every Saturday morning. So we could say, if it is Saturday morning, she jogs 5 miles. Because she could jog 5 miles other days of the week. So the way that this would actually end up being our hypothesis or our statement. So every Saturday morning she jogs 5 miles. So this is our hypothesis. This is our conclusion. So for a good conditional statement, we could say something like, and here, I'll actually write it out. Number 36, conditional. If today is Saturday, or maybe even better yet, if it is Saturday morning, if it is Saturday morning, then Koyona, I don't know how to say that, jogs 5 miles. So then, if we want to do a let's do converse first. Converse would switch it. If Koyona jogs 5 miles, then it is Saturday morning. False statement. Again, she doesn't, based on this, if this is a true statement, the other way around doesn't have to be true. So the converse of this would not have the same truth value. All right, go to the next one. Inverse. If it is not Saturday morning, then Kona does not jog 5 miles. Again, that could be true or false. We don't know. And then let's go to the contrapositive. If Kona does not jog 5 miles, then it is not Saturday. And that shares the same truth value as this. Again, conditional and contrapositive always have the same truth value. Converse and inverse have the same truth value. So those are things that are logically equivalent. All right, go on to 37. 37. Find the truth value of each conditional. Explain your reasoning. Show a counterexample. So if a number is less than 4, then it is prime. Well, are there prime numbers that are greater than 4? Yes. So that's a false statement. Counterexample, 7. 7 is a prime number that is more than 4. If 3x minus 7 is less than 14, then x is less than 8. Now, if we were to solve this, add 7 to both sides, you'd end up with 21. Divide by 3, and you would get 7. So x is less than 7. So x has to be less than 8. Well, no, there's a little gap between 7 and 8. All right? So if I had 7.5, it would not match this. So that would not work. So let's go 7.5. Again, this is a false statement. If you can find one counterexample, didn't say they had to be whole numbers. So again, this is false. Counterexample, 7.5. If it snows, then school will be canceled. Not necessarily. What if you're already at school? So again, I would say false. At school when snow started. This last one, communicate precisely. A cafeteria only offers pudding on Tuesdays. Use this fact to write a biconditional about pudding. So again, we need an if and only if statement. So it is Tuesday if and only if the cafeteria offers pudding. So if you read this as a conditional or a converse, it would be correct. If it is Tuesday, then the cafeteria offers pudding. If the cafeteria offers pudding, then it is Tuesday. Again, it works both ways. It is a biconditional statement using the words if and only if. Again, as long as the converse has the same truth value as the conditional, it can be written as a biconditional. Alright, on this side, deductive reasoning. So we got law of detachment, law of syllogism over there. Again, a few extra notes. Assume the given information is true. If AB is equal to BC, then DE is equal to this. AB is equal to 6, and BC is equal to 6. What can you conclude? Well, they gave some information here. They said AB is equal to 6. BC is equal to 6. So that matches this first part of the statement. So this is an example of law of detachment. The information given matches the hypothesis of the true statement. So then we should be able to conclude this part of our statement. So then DE is equal to 2 times AB. All right? And we could leave it at that. Or if we wanted to, we could even plug in 6. So we could conclude that DE is equal to 2 times 6. And if you want to go even further, you could then say DE is 12. Or if you just wanted to restate this statement, that would be fine as well. So there's more than one correct answer there. On 42, if it is a sunny day, the water park is filled with people. If the water park is filled with people, the lines for each ride are long. Use law of syllogism to write a true conditional. So the part that got repeated was the water park is filled with people. So get rid of that part and combine the if and then of the others. So if it is a sunny day, then the lines for each ride are long. All right, communicate precisely. An advertisement says that if you use toothpaste for more than a week, you'll have fresher breath. Use toothpaste 10 days. If the advertisement is true, what can you conclude? Well, you should have fresher breath. You should have fresher breath. Now, it doesn't have to be good smelling breath, fresher than whatever you started with, because it just says fresher. So again, make sure you're concluding what it wants you to, not what you think it should be. Doesn't mean you have good breath, it means you have fresher breath. Alright, this one is using our vertical angle theorem. So, since these are vertical angles, we know these are congruent. Therefore, we should be able to find x and then also find the measure of each angle. So these two have to be congruent. Set them equal. 3x minus 6 equals 2x plus 22. So you had this one. You should also know something about not only vertical angle theorem, but also linear pair theorem, because that was also a big point in the section. So you should be able to do the same thing with a linear pair as well. So set these two equal. Subtract the 2x, you're left with x. Add the 6, you're left with 28. X is equal to 28. Now, we can plug it back in. 2x, so 2 times 28, that's going to be 56. 56 plus 22 is 78. So both of these should be 78 degrees. This one, well, these make a linear pair, so these have to add up to 180. So subtract that from 180, leaves us with 102. So both of these are 102, because these two are vertical angles and they have to be congruent. Over on this one, we have 2x plus 32 equals 3x minus 5. Subtract off the 2x, add the 5, you get x is 37. If we plug it back in, 2 times 37 is going to be 74. 74 plus 32. 74 plus 32, 106. So this is 106, this is 106. These two angles would then have to be 74, because again, these would be a linear pair, so they'd be supplementary and have to add up to 180. Alright, this last one, the proof. Again, I'm not going to do a proof from scratch. The ones that you have are going to be ones that you fill in, just like what we did in class. So I'm going to stop here and post this. Good luck on the test. Make sure you study.